Imagine a world where everyone were gingerbread cookies. And that means that we could replace damaged or worn out tissues by just baking new ones. Pretty awesome, right? Wait, what? Turns out that we might be going towards a similar reality right now. And yes, I'm not kidding. Hey guys, it's Yalim, and today I'm going to tell you guys about how we can make brand new tissues with tissue engineering and what you should expect in the future. Let's get right into it. Most, if not every human disease comes from some type of tissue damage. And if things get really bad, the only way to cure the disease is to replace the damaged tissue with a new one. But the only way to do this right now is by organ transplantation. But there is only a limited number of organs that can be donated to people who need them. So for example, every 1 hour, one person dies because they don't get the organ that they need in time. And this made scientists wonder, what if we could just make brand new tissues? And this is how tissue engineering was born. So, scientists looked at how nature creates tissues. And it turns out that the cells initially get signal from the outside environment that tells them to multiply, differentiate, and release something called an ECM, or the extracellular matrix, which is a glue that binds the cells together into a uniform tissue. Inside a biological tissue, the cells receive nutrients, communicate, and cooperate with each other by sending molecules across the cellular glue. And when a tissue gains its biological function, what happens inside is that the cells begin cooperating with each other in response to signals from other tissues, also communicated through this cellular glue. From this, we see that this ECM, or the cellular glue, plays a crucial role in the formation of a tissue because it keeps the cells together into a uniform tissue, it keeps the cells alive, it also allows the tissue to biologically function inside the body. And this is why tissue engineering uses something called a bioink, which is a mixture of living cells and organic hydrogel, which mimics this function of an ECM to make tissues. In the intro, I was half lying when I mentioned the cookie analogy, because it turns out that making tissues in tissue engineering is actually pretty similar to making cookies. First, morphing the dough, and then baking it into an actual cookie. First, you have to morph the bioink, or the dough, into the shape of the tissue that you want to make. And in tissue engineering, we use a 3D printer called a bioprinter, which essentially deposits the bioink into the 3D shape of a tissue. And a really common type of bioprinting method is called extrusion-based bioprinting, where the bioink is loaded into a syringe and it is pushed out of the syringe nozzle by a plunger. After this bioink has been extruded out from the syringe, it undergoes a chemical reaction called cross-linking, which is when the molecules making up the hydrogel precursor, which is added to the bioink as the ECM substitute. So the molecules making up this precursor form bonds between each other, forming a net that traps water molecules in between. And this turns the hydrogel precursor into a hydrogel, so it turns from a liquid state to a gel state. And to assist with this process, commonly small molecules called cross-linkers are added either to the bioink or the environment that the bioink is extruded into. This tissue-shaped end result from bioprinting actually establishes the shape that the new tissue forms into, and this is why we call this structure a tissue scaffold, just as the scaffolding of a building. Now we have this completed tissue scaffold, we have to bake it in an oven. And in tissue engineering, we use a cell oven called an incubator, which regulates conditions like the temperature, humidity, pressure, and oxygen concentration to mimic the internal environment of the patient's body. And the tissue scaffold can also be placed in what's called a bioreactor tank, which exposes the cells inside the scaffold to mechanical pressures like compression as well as shear stress to make it even more realistic to what it would feel like to be placed inside the patient's body. Wait, it feels like we forgot about someone. The cells! Remember, there's cells inside the scaffold, so we need to keep them alive. And to do this, we submerge our tissue scaffold into a solution called the cell media. The cell media contains nutrients like glucose and amino acids, as well as growth factors that tell the cells to form a unified tissue. And over time, the nutrients and growth factors from the cell media diffuse into the tissue scaffold, reaching the cells and allowing the cells to multiply as well as secrete their own ECM to replace the hydrogel that's originally in the tissue scaffold. And it also encourages the cells to form signaling molecules on their own to send to each other and encourages the formation of a functional tissue throughout the scaffold. Obviously, tissue engineering has the potential to solve a lot of big problems in the world, like the lack of donor organs for organ transplantation, as well as organ trafficking. But there are still problems that we still need to solve in tissue engineering to be able to make brand new organs for patients all around the world. One major problem with tissue engineering is that we actually don't know how a tissue scaffold turns into an actual functional tissue. And it's almost like we know what cookie we want to make, we just don't have the recipe to it. And because of this problem, we haven't been able to make a fully functional organ with tissue engineering yet. Another problem is an ingredient that goes into the cell media that we use for cultivating our tissue scaffold, and it's called the fetal bovine serum, or the FBS, which is used to provide growth factors to cells in the scaffold. And the problem is that it's actually the blood of an unborn baby cow, or the fetal bovine blood. And this obviously has a lot of ethical reasons, but it's also really expensive. So scientists are currently looking for ways to replace this ingredient. Another large problem is that the size of the tissue that we can make right now is pretty limited. So as I mentioned before, we're depending on diffusion for the nutrients and growth factors in our cell media to reach the cells inside the scaffold. But the problem is that there is a limit to the distance that these molecules can travel through the scaffold to reach the cells. And this means that some cells that are certain distances away from the surface of the scaffold end up not getting these nutrients and die away. So scientists are looking towards solutions like embedding blood vessels inside our scaffold to solve this problem. With tissue engineering, we'll be able to live much longer and healthier because we can replace any damaged tissue that make us get older with new ones. And yes, our lives would be much more crunchy. Hey, I hope you learned some things from this video, and if you'd like to learn more about how tissue engineering works, feel free to check this article out where I review the whole process of tissue engineering. See you in my next video. Bye!